Okay, so in the MythBusters video, they had 50 people, and 2/3 of them got a CDON, and 1/3 did not. And then they gave us these numbers: 29% and 25%. And the narrator says, "There's little doubt. It does seem like yawning seems to be contagious." Okay, so I just tried to figure out how they got 29 and 25%, and it works out this way: in the CDON group, 10 people yawned. And in the no CDON group, 4 people yawned. Okay, so 10 out of 34 is 29%, and 4 out of 16 is 25%. And what do you guys think? Is that convincing to you? No, it's not. Not really convincing, actually. And we can do this. We can kind of retest this hypothesis using a randomization test. Sorry, I don't like the sound of this thing. So we're going to use a randomization test, and basically what we're going to do is, with the randomization test, we're going to take all 50 people, okay? And in the 50 people, we're going to say 14 of these people we're going to say they were just destined to yawn no matter what, okay? Whether they were put in the CDON group or whether they were put in the no CDON group, these 14 people, if you just stuck them in a room, they were going to yawn, okay? And it had nothing to do with which group they were put in. These 14 were just going to yawn anyway. And so the question is, if I take these 50 people and then I shuffle them up, and I put some in group A and some in group B, would I get a proportion of 29 versus 25? And if so, how often does that happen, or how often does something like that or something more extreme happen? Okay, and so rather than depend on some kind of central limit theorem or something, we're just going to say that if the null hypothesis were true, if yawning is not contagious, that 14 people were just destined to yawn either way, whether they were put in one group or another, okay? And so here is, let me just I'm not able to copy this code here. What's going on? Okay, so here, hang on a second. I apologize. This is not the correct script. Let me just. This is I'll fix this up. Okay, so here is our data, okay, and I'm just creating a true-false vector. Let me just clear everything out here, okay, and we're going to say yawning. I'm going to have 10 true followed by 24 false, and then 4 true followed by 12 false, okay, and so yawning looks like this, okay. And then I'm going to say the first 34 were put in the treatment group, and then the last 16 are put in the control group. So this is what we get in the MythBusters video. Is we have this for the treatment group, we have 34 values, and those for the control. And then if we ask what is the mean of the treatment, we coerce these into ones and zeros, and we get 10 out of 34, which is 29%, and the mean of the control group, 4 out of 16, we get 25%. So our observed difference is going to be mean of the treatment minus mean of control, and we have a difference of about 4%. Okay. With the randomization test, okay, I'm going to just randomize this vector. Okay, so yawning again is the vector of 50 values, okay, where the first 34 represent group A and the last 16 represent the other group, okay, I'm going to just randomize this. I take sample of yawning, okay. So sample yawning, if you use sample, it's it just means shuffle. We have 50 values and we're going to shuffle them, okay. So this is what my randomized group looks like, okay. So I've got a bunch of falses and trues, and these are all mixed up, okay. So I've just taken my 50 cards or 50 people and I've just shuffled them around, and now I'm going to just randomly, or I'm just going to take the first 34 of these shuffled people and put them into group A, and I'm going to put the remaining 16 into group B, okay? So who ends up in group A and who ends up in group B has nothing to do with whether they got a seed yawn or no yawn. It's just they just ended up in group A at random, and these people ended up in group B at random, and we're just going to say in the beginning of 50, 14 of these people were just destined to yawn anyway, right? Okay, so now we take a look at the mean of group A, and in group A, 23.5% yawned, and in group B, 37.5% yawned, okay? So in this case, my random difference is negative 14%, okay? So this would be in the seeded yawn group, or this would be equivalent to saying in the seeded yawn group only 24% yawn, and then in the no seed yawn, 37% group. So we're getting a difference of negative 14%. Okay, and with the randomization test is we would repeat this process of randomization many times. Okay, so here I'm going to just do it 5,000 times. Okay, and I'm going to create a vector called differences. And for each iteration, I just take our vector yawning. This is the original yawning vector. And I'm going to just shuffle them up. And then I'm going to put the first 34 that are shuffled into group A, the remaining 16 into group B, and we're going to calculate the proportion of group A that yawn, the proportion of group B that yawn, and take the difference. And we're going to store all of those differences. Okay? And so now, so that runs, and now it's done, okay? And we can see, here's the summary of the differences, okay? And so, one time we got a difference where one was 50 points higher, 50 percentage points higher. The first quartile is about 50 percentage points lower. First quartile is around 5% lower, percentage points lower. This is 0.44 percentage points difference and things like that. Okay, so the question is, what is the probability of observing a difference as large as our data's difference? Okay, because this is if the null hypothesis were true, which is what we've done, how often do we get a difference of basically 4 percentage points? Because that's what we observed. We observed 29% versus 25%. How often our observed difference is 4.4 percentage points. How often does this happen? Okay, all right, with our one-sided test, it happens over half the time of getting a difference of 4 percentage points or more. Okay, so if we just shuffled the people at random and threw some group, 34 people into one group and 16 into the other group, knowing that 14 of these were destined to yawn anyway, there's over a 50% chance that just from randomness we're going to get a difference of 4 percentage points in one group versus the other group. Okay, so it seems a decent probability. It's just there's a very high probability that the difference that we observed in the Mythbusters video is a result of random chance alone. Okay, this is that's what we get. Okay, so so the Mythbusters video, we had 50 people total, 14 Yan total. Okay, and what we had was 10 out of 34 in the treatment group, which is about 29.4%, and 4 out of 16, which is 25% in control group. Okay, under the null hypothesis, 14 out of 50 are destined to yawn. Okay, and we randomly assign 34 people to group A, and the other 16 to group B. Okay, so now we know the association between yawning and group assignment is just pure chance. It's purely from random assignment. So what we do is here's our our randomization test code, and according to this is what we would have done. A one-sided test reveals that over half the time, okay, because we want to know how often are our differences greater than or equal to our observed difference. This says that happens over half the time. Okay, and if I do the absolute value of the differences, I get 1. Which means if I just said, what's the probability that one group ends up being 4 percentage points more likely than the other group, that happens every single time. Because the proportions are different, right? You have 34 and 16 in one group. If I just kind of switch things around, instead of 4 out of 16, so 4 out of 16 is 25%. If I put one more and I did 5 out of 16, I would have 0.3125, which means the other group would be 9 out of 34. Okay, this would give me a difference of, what is that? A difference of 4.7 percentage points. Okay, that's a greater difference. If I switched it around and I said 3 out of 16 versus 11 out of 34, that gives me a difference of 14 percentage points. Okay, so it's actually impossible to get a difference that is smaller than 4 percentage points. Okay, like it is not possible to get a difference that's smaller than this. So when they say, well, it's not big, 29 versus 25%, they say, well, that difference isn't dramatic, but because our sample size is big enough, I feel like the myth is confirmed or whatever. Actually, that difference of not being dramatic, that is literally the smallest possible difference that can happen when you have a group of 50 people where 14 of them are going to yawn and you split them into 2 groups. It's not possible to get anything smaller. And so when we did this, and if we were just looking at the absolute value of the differences, you get a p-value of 1, meaning with probability 1, you will get a difference like the one you observed or something more extreme, okay? So what we observed on Mythbusters is not convincing at all, okay? Technically, MythBusters was using a one-sided hypothesis test because they wanted to know if somebody yawns, are you more likely to yawn? Okay, and it just seems that they happen to get lucky in flipping like heads in that just by chance maybe they happen to get a higher proportion in the yawning group than the no seated yawn group. Okay, which there you go. So that's the randomization test. I guess on Thursday we will pick up and talk about the bootstrap test, the non-parametric bootstrap test. But we'll cover this concept of kind of computational statistics. Doing these hypothesis tests without math, but depending on the computer's randomization here. Okay, we'll wrap up here. We'll see you guys on Thursday.